Okay, it's day 16 of Advent of Code, but this video I'm doing something a bit different because this is not the first solution, but I'm not going to upload a video that's 2 hours long of me fumbling through a solution. Nobody wants to watch that. So this one's a little bit different, and I might do a bit more of this actually with future ones, because as Advent gets a little bit harder, I don't want to be uploading like hour-and-a-half videos of you watching me gradually work through the problem. So let's see. For the easy ones, I'll do them completely live. And then in some cases, if the video gets too long, I'm just going to throw it away and instead just walk you through what I've actually done, just in the interest of not having really long videos. So let's jump into this, and I'll show you day 16 and my solution to day 16. So this is a bit more of a walkthrough, this video, rather than a let's solve it together from the start. Okay, so here we are. Day 16. Now, of course, I've read through this now, so instead of reading through it word by word, essentially I can explain it much more simply now. We have a maze, and yeah, we have a maze. And this maze, we have a start position and an end position, and the idea is simply to, first of all, solve the maze. So it's a pathfinding exercise, and then, so here's an example. And then basically what we need to do is calculate a path that is considered to be the shortest path, but not according to length, according to cost. And the cost is that any forward movement, or a movement in the direction that you're already facing, is considered a cost of 1, but a turn, a 90-degree turn, is considered a cost of 1,000. So it's pretty clear, at least at this point to me now, that that's what this is weighted towards. No pun intended. This exercise is all about figuring out the shortest path with regards to turns, since those turns are much more expensive than a movement is. It's about reducing turns, basically. So they give us an example here, a small one, then they give us another bigger example here and give us 2 answers, so we can use those to orient our solutions. And then we have our own puzzle input. Now, I've not put the puzzle input answer in here. I've been solving the smaller one, so let's jump over here. So you'll also notice here that this particular solution is in JS. That's just because I've taken away all the type signature information here, so I can explain it a bit more simply without spending too much time talking about Typescript. So here's the basic one, the first example I should say, and I'll talk through the solution, but let's just let's just talk about the easy things first. So we read from the text file as we've done in all the other videos, easy. We break it into a 2-dimensional grid, exactly the same as we've done in all the other videos, nothing special going on there at all. And then if we there's a search function here being defined, and it ends right down here. So all of the behavior is inside the search function. I've tried to clean this code up as much as possible, since you're not going to see me walk through on camera writing this. I've cleaned it up before talking about it so we can go through it more easily. And then essentially this is the call site here. We just call out to the search function, we pass it 4 things and log its response. Now what we pass it is, so if I just jump up to here, what we pass it is the starting y and x position and the ending y and x position. And those are really easy because if we just take a look at this sample, we can see the s is there and the e is there. So there's no point in writing code that finds it. If you were writing a general solution, you would write code that searches for the start position, the end position, so that they could be moved around and you could solve any maze that you were given, but we're not solving any maze, we're just solving this one. And whatever the actual puzzle input is, I'll just figure out what those coordinates are and put them in manually. I'm only interested in getting the answer here. So yes, what we do here is, because it's in the bottom left, it's the grid length -2, because we're sort of skipping the wall as well. So it's not the last row, it's the last row -1, or -2 from the edge of the grid. And similarly on the x, it's also 1, it's just 1 in from the edge, and it's basically the reverse in the other top corner. So those coordinates are predictable, we can just put those straight in there, there's no point in adding more code. And then, okay, so let's talk about the solution. My first attempt at the solution actually was to do a depth first search, a DFS, which we've done in previous videos for finding all possible combinations of things. They're usually written in a recursive way. And I couldn't really make that work cleanly, so and this is what's good about Advent. Some of these Advent solutions make you go away and think about a different solution approach to the problem. And in this case, it's a breadth first search with a priority queue that I've gone down that route instead. which is better because it's a lot more efficient as well. Because we're trying to find the shortest path. So there's lots of different ways to do this one. There's Dijkstra's algorithm we could use as well, and this isn't too different from Dijkstra's algorithm, a breadth first search. These are good algorithms to have in your head for those probably very rare occasions where in day-to-day programming you actually need them. And by the way, I'm kind of done now with two-dimensional grid problems in Advent of Code. Let's get something a bit more interesting. Let's get something a bit more challenging. Well, actually, this is challenging, but it's been challenging in this way quite a few times now. So, little rant over there. Okay, so what we start with here is this search function is not recursive, because a breadth first search is a different algorithm. What a breadth first search does is take a position, and then it looks around that position to the other neighboring locations, and pulls out those locations and puts them onto a queue. And then it does that for each of those locations. And so you can see it's kind of recursive in that sense, but it's not written in a recursive style. It just pulls out all the things and puts them onto a queue. So we've got this, sometimes called priority queues as well. So we've got this queue here, which is just my own doing, because what I'm trying to keep here in each position of the queue is where we started, what the current path is. I need that because I need to know what the length of the path is, because that's part of, I didn't explain it properly here, but once we found a path, we need to calculate the cost, the score. And the score is the number of turns that were made and the number of steps forward that were made. Step forward scores as 1, turns are scores as 1,000. So we need both of those numbers. So the path is an array that we'll just put the various different positions onto as we work through it. I need to keep the direction because I need to know if the direction changes, because if the direction changes, then we need to know that it has, so we can increase the turn count, and the turn count's going to tell us, the turn count plus the path length is basically the answer. So so we create this queue. This is a little bit of setup that we're going through here, and then we create this visited map. No surprises there. We want to make sure that as we spread out the this breadth first search, this BFS algorithm, that we don't go back to cells that we've seen before. But there is a little exception here. We don't want to go back to cells in the same direction. We can go back to cells in a different direction, but not in the same one. So you'll see in a second what I do about that. Then, as per all the other ones, all the other videos where we've done this two-dimensional geometry stuff, we capture the different cardinal directions that we can move in here on the 2D space. So this is y and x just represented as an array here, nice and simply. And then there's also a function here that can tell us whether a position, a new y and x position is valid. And again, we've seen this written in other videos too. We've written this in the other videos as well, which is just checking that the y coordinate's greater than 0, the x coordinate's greater than 0, and both y and x are greater than the grid boundaries. And in this case as well, knowing that grid yx, the location of the grid, is not a wall, because if it's a wall, we cannot move to that position. We can do a turn, but we can't move forwards. So valid captures that logic for us. And then basically this is the crux of the algorithm. Now this isn't actually that long, so I'll be able to explain this pretty quickly. So we have this queue, and the point of a breadth first search is basically to keep adding to the queue and processing off the other end until it's empty, or until we found some other favorable condition that we're trying to find. So it's a simple while loop that's making sure that we're going to continue iterating until it's empty. And what we're going to do each time is the reason we've got this sort here is this is what makes it the priority queue. Is that what we've got on this queue is all of the different positions that we've discovered, or that as we're discovering them during this algorithm, during this BFS algorithm. And it's not important to us to process anything other than the shortest possible path, but the shortest possible path with regards to the turn count, not the number of distinct collections of yx coordinates. We're not trying to find the shortest path in the traditional sense. We're trying to find the shortest path in the sense of how many turns did it include. So because we count in the turns up each time, which we do down below, we want to make sure that we're pulling off the queue the thing that has the smallest number of turns so far, because we're trying to find the best one. We're trying to find the shortest, cheapest path, basically. So what we do then is we say, okay, pull off the queue, off this priority queue, the next thing, we'll call that current. Grab y and x from current. Current is current dot position is the y and x, and current is what we just looked at here. It has all this information inside it here. So we pull off the current one, and then the first check is to bear in mind this we could be in iteration 1000 of this loop. We want to make sure that we haven't reached the end. We may have reached the end coordinate. If we have, then what we want to know next is if we have a best. If we don't have a best, if it's the first one, for example, we need to make sure it's set. So that's why the not best is there. It's a bit of a sort of edge case. What we want to know though is if the current turn that we've been working on, or the current path that we've got, if the turns in that path, if we've reached the end, the path has just finished. So we've gone from the start, we found the end, and we want to know if the number of turns that we took in this were less than the number of turns in the previous best path. If so, update the best path to the current one, and we found the best one. So we'll just continue over that one. We're continuing because we wait until the queue is empty. We don't know that this is going to happen again in a second, for example. We don't know it's the last one. So we don't break out of here. We need to carry on iterating to allow this continue to find a better path than even the best one that's just found. And then if we're not at the end, then yes, we just need to keep exploring the neighboring positions around this cell, and the first part of that is to say, okay, have we been here before in the same direction? And this is the important thing. So we say with y and x here, we would normally in previous videos we've just captured y and x, and we've said if we've got something in some kind of map that tells us we've been at the cell before, we're done. In this case, there's a slight variation on this, which is I'm adding the index of where the current direction is. So the directions is just an array, right? I'm just calling index off to get the literal zero-based index of which particular index we're in here, which direction essentially we're facing. And then that'll be a value in there that's either 0, 1, 2, or 3. And if we don't have 1 at the moment because it's the beginning, then it's -1. All that means is that we're keeping 3 elements as the history of where we've been on this 2D grid. And that's the y, the x, of course, and the direction. We can go to the same y and x in a different direction. That's valid because we're trying to pathfind through this grid. So then we say, well, if we visited here before, continue again. We don't want to do this again, so just skip over, go back to the top and go over again. However, if not, then let's make sure that we actually mark that we have visited here. So we set that key in there. And then this is the important bit. Bear in mind this is inside the loop. So we're now going to say, right, well, we've got 4 directions that we can move in theory. We're going to allow that valid move to tell us whether we can or not. So we calculate the dy dx, we calculate new yx, a new y, a new x, and both of those are basically the current position plus the delta from the specific direction. We're considering all 4 directions from the place we're at right now. Again, valid is going to tell us whether that's off the grid or whether it's a wall. And if it is any of those conditions, we'll just skip again. We'll skip this particular 4. However, if it's not, then it's a valid position in the grid that we've not yet reached the end of. So what we do then is produce the next element to put into this queue. The next element's going to be a y and an x in position-wise, which is the new coordinates we've just calculated. The path is the current path plus the new coordinates. You've seen this, I've done this in every other video so far. The only difference is this is an object on a priority queue that's being pulled off. The direction is whichever direction that we're in. That's going to change as we go through each one of these. And then turns is whatever turns currently is. And then we need to make sure that we update turns if we've turned. So this little bit here is probably the only sort of like weird thing, just because of the way I've written this. But if we say in here basically that if we have a direction, in the first instance we won't have one, for example. So again, that's just an edge case to make sure we don't crash out. And then what I'm doing here is just saying, take the current direction, convert it to a string. That's literally just going to be like a string that contains a bracket with like 1 and 2. And well, it won't be 1 and 2, it'll be like 0 and 1, or it'll be like 0 and -1 or something. So we get the string version of it, and we say if the string version of the current direction is not the same as the string for the direction that we're now going in, then this is a directional change. In which case, before we put next onto the priority queue, just make sure we update the turns by 1. That's really important because that's obviously we need to track turns. That's the one thing that we're not only tracking, but this priority queue is reordering the queue according to turns to choose for the smallest path, the cheapest path. And that's it. That just goes round and round and round, and then once we're done, it'll return whatever was last left in this best variable that we've got up here, best, which again is being assigned to here. When we reach the end of the grid, or the end position, if the amount of turns that we've accumulated by then is less than what the previous best was, we assign to it, and so we know it's the best. So that's it. Now if I, so the grid I've taken to be their, their example, which is this one here, and they tell us here it's 7036. So if I run this, then what I'm doing here is I'm just outputting the best. This is the object best that we were talking about. So that was the last position that we reached. That's the path, and then we've got the number of turns there. Now when I was going through this, I thought that I'd actually not solved the problem properly, because turns should actually be 7, which it tells us there. It says there's 7 turns and there's 36 steps. Now there are 36 steps because we've got 3 here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 times 3, 36 steps. So we've got the 36 times 1 bit right. The turns is 1 off though, and the reason it's 1 off, which took me a second to realize, which made the previous attempts way too long to put into a video form, is because it does mention that in here that you will face east to begin with. So S in this case is facing east, but the algorithm starts by just simply with no direction. So it performs turns immediately, and it doesn't count that first turn. So it's just basically off by 1, which is not really a big deal. It's always off by a 1, so we can just add 1 to it, but there's no point in even doing that. It's simply turns plus 1, which is 6 plus 1, multiplied by the 1,000 cost, and then plus, and then we're going to plus the 36 steps, the length of this path. Precedence, 7076, which is exactly what it should be. So if let's take their second example, which I've not tried, 11048. So if we just put this in here, in this import here, paste over that. Yep, slightly different grid now, and then let's run that one. Okay, I'm not going to count all those manually, so actually let me just update this code a little bit to say we'll output res, and then we'll output console.log res.paths. Well, I may as well do the calculation here, res.paths.length, so that we're going to, it's res.turns plus 1, as we just said, that should be off by 1, multiplied by 1,000, and then plus that, so it's 2 here. Oh, I'm trying to be helpful but not being. So let's do that again. Oh, it's not paths, it's path, sorry. 11048. Okay, cool. Yeah, so it's working. All right, so let's get the puzzle input then, and let's see if it actually works for the big one. If it doesn't, might be doing. Oops. That is probably not right. Let me just get rid of, I don't want to make a mistake here, so let me just get rid of all of it, copy that one again. Just set no wrap here. Yeah, looks like a grid. Now, are we in the same position? S down here, I hope so, because then I don't have to change the, yeah, I had a feeling that would happen. Okay, cool. So we're in the same position as before. All right, well, okay, we've got a number. Doesn't look very big, but let's see. That's not the right answer. Okay, let's see what's going wrong here. Okay, let's see. This grid is definitely well formed. Yes. It did look like a smaller number to me as well, so I'm not sure what's wrong there. Coordinates are the same. This calculation is right because we just tested it with a smaller grid and it was okay. So res.turns plus 1 multiplied by 1000 plus res.path.length. Yes. Let me actually see what's inside res here. 528 more items in there. 147 turns. So we're saying that's 148,000 plus 5 to 8 and whatever that is. That's roughly what the answer was, 148,628. Yeah, okay. Unless, of course, we don't need the +1 in this case because it moves. Does it? There we go. So possibly the correct path. Well, yeah, clearly that path not correct. So maybe the +1 assumption that we made there doesn't apply here. I've not written any code here to deal with the assumption about its starting position. So let's try that one again. We have a number now 147. Yes, just one turn less. 147. So I don't know if I'll be able to submit this yet, but there you go. Okay, yeah, that's interesting. Yeah, if you don't capture this detail in the code, then basically it's sort of like an edge case. It's like, do you turn or do you not turn to begin with? Technically you're facing east, and if that's the path that ends up being a successful one, then you don't need the turn. So I hadn't put that into the code at all. I wasn't dealing with that detail in the code, but that makes sense. There we go. That solves it. So this is a nice short video compared to what it would have been if I recorded the whole thing, and this would have easily been an hour and a half, maybe even longer. So I think this is the way to go for some of these Advent challenges that are quite methodical, and those that require sort of the implementation of an algorithm that doesn't just sit there in the brain for for all of the time, and you're just like, oh yeah, I need a depth first or a breadth first search, I'll just go ahead and code it. You have to think about it. So but anyway, yeah, that was a relatively challenging one. It's not a trivial one, and it's hard to brute force it because that grid's very big. I can't imagine how many possible combinations there are through this grid. So if you do depth first and you just try and find every path, you can easily run into situations where it just doesn't execute in a timely fashion, especially in a language like maybe JavaScript, or depending on how you implement it, if you're keeping a lot of memory around in a recursive depth first search, then yeah, you're going to just either run out of stack or potentially just run out of memory or just wait too long for it. The breadth first search is a nice algorithm here, and I think that's one of the good things about Advent, is at least you sort of, it's probably one of the few times as programmers that we actually get to play around with algorithms and just data transformations. But like I said at the beginning, I'm very happy to move on to different kinds of problems now. Wink wink, nudge nudge, Advent of Code people. Give me something more interesting. I'm sick of doing 2D geometry, okay? Alright, end of the video, and I will see you for tomorrow's day 17.